Hello everyone, so today I'd like to talk a little bit about implicit differentiation. So here the key idea is that x and y might be related by some kind of equation. So the equation would define, say, a curve in the plane. So we should still be able to find dy over dx and slopes of tangent lines and all that kind of stuff. But we might not be able to solve our equation explicitly for y in terms of x. So if we can't solve for y in terms of x and then just differentiate to get dy over dx, what should we do? Okay, so here are some examples. So as we said, x and y are related by an equation, and y is defined implicitly in terms of x. So notice that's different from explicitly where we have y equals. So implicitly means we have some kind of equation involving x and y that they have to satisfy. So here, for instance, x squared plus y squared equals 25. Then, as you probably know, that describes a circle that's centered at the origin with radius 5. And okay, if we plug in different values of x, then we can solve to get different values of y. But if we were to try to solve that and put it in the form y equals something, then we would get two equations, right? We would get y equals plus the square root, and we would get y equals minus the square root. And depending on what we were doing, we would need to pick different functions. Okay, so this is one example where the y is determined implicitly in terms of x. Here is another one that's even more unpleasant. If we look at y plus arctan y equals x, then this also defines y implicitly in terms of x, right? If I have a particular value of x that I plug into that equation, then I have a constraint on what y values I can pick, right? I can't just pick any y values. They have to satisfy this equation. For instance, if x equals 0, then y plus arctan y equals 0. Well, one solution would be, say, y equals 0. So y is determined by x, but we cannot explicitly write this in the form y equals, right? Because if I were to try to take the arctan over, I would still have a y on both sides. And if I try to take tangent of both sides, I would end up with tan y plus y equals x equals tan x. So we cannot write it in the form y equals. So what should we do? How can we find dy over dx and equations of tangent lines and so on? And notice this isn't too unnatural, right? Because if we think of what these equations mean, x squared plus y squared equals 25 is a circle. So a circle has tangent lines just like every other curve. And also this strange equation describes a curve. Okay, quite a complicated curve, but okay, who cares? There are still tangent lines and so on. So it's not too unnatural to try to find dy over dx in this setting. So what is the idea? Well, the key idea is that we're going to differentiate both sides of the equation with respect to x and then solve for dy over dx. So what does that mean? Okay, we see here we have things like y squared and we have arctan y. So how can we differentiate these with respect to x? So that's our next task, to understand how we differentiate these functions of y with respect to x. So let's do that. So let's suppose that f is a function of y, where y itself depends on x. How can we differentiate f of y? Well, it's an application of the chain rule, right? So if we think of it as finding the derivative of f of y, but y is itself a function of x, right? We have an outside function f, we have an inside function y depends on x. So, okay, we have a composition, we can do the chain rule. It's the derivative of the outside evaluated at the inside times the derivative of the inside, which is dy over dx. Okay, and sometimes, we write y, we don't always write y of x, even though y is often a function of x. So if we want to write this more briefly, we can write this as the derivative of f of y equals f prime of y dy over dx. Okay, and what's the way to think about this? Well, if we want to differentiate a function of y with respect to x, what do we get? We're saying it's almost as if we were differentiating with respect to y normally, except we have to multiply by dy over dx. Okay, so that's what I wrote here. If we differentiate a function of y, we get what we would have got if we were differentiating with respect to y, but we have to multiply by an extra dy over dx factor, just to compensate the fact that we weren't differentiating with respect to y, we were differentiating actually with respect to x. Okay, so here's a couple of examples. So for instance, if we want to differentiate sine y with respect to x, if we were differentiating with respect to y, we would get cosine y, but we're differentiating with respect to x, so we have to multiply by dy over dx. Similarly, with e to the y, if we differentiate with respect to y, we will get e to the y, but we're differentiating with respect to x, we have to multiply by dy over dx. Similarly here, the derivative of y to the n, normally it would be ny to the n minus 1, but we have to compensate, so we multiply by the dy of dx. And we can combine this rule with other rules like the product rule, the quotient rule, and so on. For instance, here we have x times e to the y. It's a product. So let's use the product rule. We fix one factor, differentiate the other, and vice versa. And then we have to, it comes to differentiating e to the y with respect to x. Okay, we already saw that's e to the y times dy of dx. Okay, so we can combine this rule with the product rule and the quotient rule and so on. So bottom line, if you have a function of y and you have to differentiate with respect to x, differentiate with respect to y, but then multiply by dy of dx. And that's a consequence of the chain rule. Okay, so let's see how to apply this to equations. So here's a very simple example where we can do it both ways, but let's see that we get the same answer. So we're looking at the simple equation, xy equals 1, And it defines y in terms of x for x not equal to 0. And our task is to find dy over dx from this equation. So one method, if we don't use anything from this section, would be just to write y equals 1 over x. Sorry, here is y equals 1 over x. So we would get dy over dx equals minus 1 over x squared. Right, so we have xy equal 1, y equal 1 over x, dy over dx equals minus 1 over x squared. That doesn't use anything we just talked about. Another method would be to instead differentiate both sides of this equation. So we would fix the x and differentiate the y. That would give us x dy over dx. And then we would fix the y and differentiate the x. That would give us y. And then we differentiate the right side, which is 1, we get 0. So if we differentiate both sides of this with respect to x and use the product rule, we get the equation x dy over dx plus y equals 0. And then we solve this equation for dy over dx. So we get dy over dx equals minus y divided by x. Okay, but since, and they look kind of different, like in method 1, we got minus 1 over x squared. In method 2, we got minus y over x. But we have to remember that y was equal to 1 over x from our equation. So these are actually the same if we sub in y equals 1 over x. Okay, so both strategies give us the same answer. But in more complicated examples, we can only use method 2. So method 1 relied on first solving for y in terms of x to get y equal 1 over x. With more complicated equations, that's not always possible. Okay, but if both methods are possible, then they give us the same answer. So kind of everything is good. If we got two different answers, that would be very bad, right? So here's a more complicated example. So let's look at x squared plus y squared equals 25, the circle again, and try to find dy over dx and use it to find the equation of the tangent line at 3, 4. So let's use method 2, because if we were to try to solve for y in terms of x, we would have to take square roots, and we would have to choose the positive or the negative. There would be two choices, and then we would have to use the chain rule, and so on. So let's just differentiate both sides of our equation. With respect to x, if we differentiate x squared, we get 2x. If we differentiate y squared with respect to x, okay, if we were differentiating with respect to y, it would be 2y. And then we should multiply by that extra dy over dx term because we're differentiating with respect to x. So the derivative of y squared will be 2y dy dx. And then we differentiate the 25. 25 is a constant, so we get 0. Okay, so differentiating an equation like this gives us a new equation, which is still true as long as we differentiate everything correctly. So now we get the equation 2x plus 2y dy dx equals 0. Okay, and now this equation is simple to solve for dy dx, right? Dy dx is going to be minus 2x divided by 2y, so minus x divided by y if we rearrange. Okay, and now, well, if we're going to find the equation of the tangent line at 3, 4, we have to find, okay, we know the point on the tangent line, we have to find the slope. So we're trying to find the slope, which is dy dx at x equals 3 and y equals 4. So now we can substitute both the x value and the y value. So, all the examples before, we had dy dx just in terms of x. Now we have it in terms of x and y. But luckily, we know the values of x and y. We can sub them in. We get dy dx equals minus 3 over 4. Okay, so we use point slope form for the equation of the tangent line. Y minus y1 equals mx minus x1. So we get y minus 4 equals minus 3/4 x minus 3. Okay, so just to say it again, so we had an equation. We're trying to find dy dx. If it's hard to solve for y in terms of x explicitly, which is going to be true in a lot of cases. Here we could have done it, but it's a lot of examples you can't do it at all. We differentiate both sides of our equation. We differentiate functions of y implicitly. So we have to multiply by that extra dy dx factor, and then we solve for dy dx. Okay, and notice, by the way, here dy dx equals minus x over y. This formula works both for y bigger than 0 and for y less than 0. Whereas if we'd solved our equation at first to find y equals plus the square root of 25 minus x squared or minus the square root of 25 minus x squared, we would have had to choose one sign for y bigger than 0 and one sign for y less than 0. So even in this simple example, it unified everything. Okay, another type of problem could be to find higher derivatives. So let's suppose that x and y are related by sine y plus cosine x equals 1. And let's find the second derivative of y with respect to x. Okay, so we could try to write sine y equals 1 minus cosine x and take arcsine of both sides, but we still don't know the derivative of arcsine just yet, and that would be a mess. So let's differentiate implicitly. So we differentiate both sides of our equation. Derivative of sine y with respect to x, it's going to be the usual derivative, but we have to multiply by dy dx. So that's going to give us cosine y dy dx. Differentiate cosine x as usual, we get minus sine x. Differentiate the constant, we get 0. Right, so we start with our equation and we just differentiate both sides with respect to x, and we get a new equation. And then we have to solve this equation for dy dx. So we're going to take the sine x over and divide by cosine of y. So we get dy dx equals sine x divided by cosine of y. So this is dy dx, but we wanted to find d squared y over dx squared, so we want to find the second derivative. So the tactic now is to differentiate both sides of this. So if we differentiate both sides, okay, on the right side, we have a quotient. So we're going to want to use the quotient rule. So let's try to do it step by step. Differentiating the left, differentiating dy dx with respect to x gives us the second derivative of y with respect to x. And then the right side to differentiate, we have to use the quotient rule. So we have here the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So here I just wrote out what the chain rule says to do, what the quotient rule says to do. And then we have to actually differentiate the top and differentiate the bottom to do these actual d over dx's. So if we differentiate sine x, we get cosine x. Now we have to differentiate cosine of y. So remember, it's like what the normal derivative would be, except we have to multiply by dy dx. So we're going to get minus sine y dy dx. Okay, and we have a minus and a minus, so we are going to get a plus. So we get plus sine x sine y dy dx if we combine the terms. Okay, but now we want to get an answer for the second derivative just in terms of x and y. So we don't want this dy dx hanging around because we don't know what that is. But remember, we had dy dx as sine x divided by cosine y. So the last step is to replace any dy dx's by whatever they were in terms of x and y. So the dy dx was sine x divided by cosine y. Okay, if we simplify, we're going to get sine squared of x, and sine y divided by cosine y is going to give us tangent of y. Okay, so just to repeat what we said, if we have equations where x and y are related, and we want to find the second derivatives, the steps are to differentiate both sides of the equation, solve for the first derivative, and then differentiate both sides again. That will give us an equation for the second derivative. And any dy dx's that we have on the right side, we want to replace them by whatever we got for dy dx in the previous step. So we can get an answer for the second derivative just in terms of x and y. Okay, so let's look at one last application of this method, which is differentiating inverse functions. So implicit differentiation will pretty much allow us to differentiate any inverse function. If we know how to differentiate f, and if the inverse is differentiable, then we can find a formula for that using implicit differentiation. So in the next section, we'll see how to do that with log functions, which are the inverse of exponential functions. But for now, let's just do it with inverse trig functions. So let's remember if y equals f of x is a one-to-one function, meaning that if I have two different x's, then they go to different y's, right? They don't get mapped to the same thing. So different points go to different places. Then we can find the inverse. So the inverse is just defined by mapping backwards, right? So y equals f of x, the inverse maps y back to x. Okay, so trig functions are periodic, which means they are not one-to-one. For instance, sine of 0 is 0, sine of 2 pi is 0. That's not one-to-one, right? The different points are going to the same place. So if we want to make them periodic, if we want to make them one-to-one, we have to restrict their domain. So if I want to think of sine as being one-to-one, I can't have it on 0 to 2 pi. I have to restrict to a different domain. Okay, a standard choice is to restrict to minus pi over 2 to pi over 2. Okay, so we do that when we define inverse sine, so arcsine. So y equals inverse sine means sine y equals x. So I did sine of both sides, sine y equals x. But we have to additionally assume that y is between minus pi over 2 and pi over 2. Okay, so what are we saying? If I want to calculate inverse sine of x, that's my y, I have to look at what number. So I'm trying to find y, which is inverse sine of x. I'm trying to calculate this y. I have to find what number y that's between minus pi over 2 and pi over 2. I can plug into sine in order to get back x. And the fact that I'm assuming y is between minus pi over 2 and pi over 2 means that there is only one solution to sine y equals x. Okay, anyway, so let's try to differentiate the inverse sine of x now that we remember what inverse trig functions were. So let's try to differentiate this. Okay, right now we can't differentiate it. That's the answer, that we don't know what to do. So let's take sine of both sides. So let's rewrite it as sine y equals x. Remember we said that y equals inverse sine is the same thing as sine y equals x. And now we can differentiate implicitly because we know how to differentiate sine. We know how to differentiate functions of y with respect to x. And okay, x we can just differentiate on the right side. So if we differentiate both sides with respect to x, sine y is going to become cosine y dy dx. X is going to become 1. So we get the equation cosine y dy dx equals 1. dy dx equals 1 over cosine y. And now, if possible, we would like to write the answer back in terms of x. So we'd like to have the derivative of inverse sine x equals something in terms of x. So that means we have to write cosine y in terms of x. So we need an equation that writes cosine y in terms of x. Okay, if I have sine y, I can say that's x. So I need to be able to write cosine y in terms of sine y. And then once we write cosine y in terms of sine y, we know that sine y is equal to x. So life will be good. So we need a way to write cosine y in terms of sine y. Well, luckily we know that cosine y and sine y are related, right, by one of our much beloved identities, sine squared plus cosine squared equals 1. Okay, so let's try to solve this for cosine y. So we would get cosine squared y equals 1 minus sine squared y, and it seems like cosine y should be plus or minus the square root of 1 minus sine squared. Remember, whenever we solve an equation that's like, x squared equals something, we have to do plus or minus the square root. So it looks like cosine y is plus or minus the square root of 1 minus sine squared. But luckily, if we go back to minus pi over 2 less than y less than pi over 2, that tells us that actually cosine y is bigger or equal to 0, right? So if we're in this region, that means we're on the right side of the unit circle, and cosine is the horizontal component, so cosine is going to be positive on the right side of the unit circle. So we have to take the positive square root. So cosine y is going to be the positive square root of 1 minus sine squared y. And now we know sine y is x, so this is going to be the positive square root of 1 minus x squared. Okay, so now we managed to write cosine y back in terms of x. We can get dy over dx is 1 over the square root of 1 minus x squared. Or in other words, the derivative of inverse sine is 1 over the square root of 1 minus x squared. Okay, so we managed to differentiate inverse sine, and we get 1 over the square root of 1 minus x squared. And as you can imagine, the strategy is going to be similar for inverse cosine, right? If we had y equals inverse sine, if we instead we had y equals inverse cosine, we would write it as cosine y equals x, we would differentiate both sides and so on and make sure we choose the right root. If we had y equals tan inverse, we would have tan y equals x, differentiate both sides, we get secant squared y dy dx equals 1. Then we try to use an identity to write it back in terms of x and so on. So all of them, the strategy is the same. So here are the three kind of key ones. So we already saw how to differentiate inverse sine. The derivative of inverse cosine is similar, but with an extra minus sign. Very useful one is the derivative of inverse tangent. That's 1 over 1 plus x squared. So I recommend knowing these three. And also we can do that for the evil twins, secant, cosecant, and cotangent. Okay, they're slightly different, but the strategy to get them is the same. Okay, so what we said in the last few slides is that we can use implicit differentiation to differentiate a lot of inverse functions, for instance, inverse trig functions. And the strategy was to rewrite it as an equation, not with the inverse function, but with the original function, differentiate implicitly, and then try to rearrange to get an answer in terms of x. Okay, that's it for this time. Thanks, everyone. See you next time.